Welcome back to elementary statistics. In this video, we're going to talk about how to use the standard deviation in order to gain more knowledge about a distribution. Before I get in, I want to remind you that we've talked about the mean and the standard deviation, along with some other measures of skew, otherwise the shape of the distribution, other tools of central tendency, the median, the mode, the mid-range, other things. But very specifically for the mean, the variance, and the standard deviation, we use slightly different symbols when we're talking about the entire population compared to when we're talking about a sample. I'm going to use those kind of fluently throughout the rest of the course, and you need to be able to recognize pretty quickly when I'm talking about a population or a sample. For right now, the things we're doing in this video, you're going to see the same formula show up twice, once using the population variables and once using the sample variables. In the future, we're going to be looking at some concepts that are going to involve the population variables and the sample variables in the same equation. And so getting used to the difference and getting used to which one means which is important. It's something that I want to introduce early and think about often, so when we get to it later, it's going to make sense. Right? Again, this video tends to make that not so obvious as something we're going to care about, because for the most part, we're going to be looking at concepts where we could use either the mean and standard deviation of a population or the mean and standard deviation of a sample, and the rest of the formulation works just the same, right? That's let's ease into all of the statistical work. That's not a, this is how they're used. All right, let me get my head out of the way, and let's talk a little bit about what standard deviation does. We've looked at several kinds of frequency curves in the past. We've looked at the difference between a curve that has some low outliers. I'm sorry. Try drawing these and saying them at the same way. Curves that have high outliers. Curves that have low outliers. Curves that are fairly symmetric. Those ideas deal with the skew. We've also dealt with some curves with these ideas of mean and the other forms of central tendency. So if we take a curve, let's try drawing a little bit of a nicer one. There's a pretty nice one. If we take a curve that is fairly symmetric, and we talk about the different places it could appear compared to the axes, these pictures are both symmetric curves, but they are shifted to the left and right. That's something we can describe using the central tendency. Right? The mean, in this case, for this particular shape of a distribution would be nice. Other shapes of distributions, the median, the mode, the mid-range might be more valuable. The standard deviation is one last control that we have over the shape of a distribution. The standard deviation is intended to allow us to tell the difference between a tall, skinny distribution and a short, wide distribution. All right. So the measure of the standard deviation is related to how wide the distribution is. I can change the look of this distribution by talking about changing the scale, right? Very simply, I have my 0 point as a control here. I could put 1 here or there just as easily. So looking at the picture alone doesn't really tell us what's happening. But that idea of how far out is the distribution is going to be the thing that we're looking at. And so I like leading off with exactly that. We call this the empirical rules. If I take a distribution, and I'm going to make some assumptions about the shape of the distribution, which may not seem obvious at first that they are things we can assume easily, but they are things we can assume easily. And so I'm happy to make these assumptions. Let's assume that we have a fairly symmetric distribution here, and that the mean of the distribution falls right at the center. Now, what I want to do is I want to take steps centered around the mean of the distribution, kind of like this, so that the length of each step is the size of the standard deviation. So this point here is going to be the mean plus the standard deviation. This mean, or this point over here, is going to be the mean plus 2 times the standard deviation. And then the third point is going to be the mean plus 3 times the standard deviation. In a population, we're talking about mu plus some number times sigma. And so when you're talking about it in terms of a population and using sigma, that's where a phrasing comes in, a difference of 3 sigma or a difference of 5 sigma, 3 times the standard deviation or 5 times the standard deviation. And that's useful to us because it turns out that if we shade in and think about how frequently do scores fall into this range, we get some numbers that are surprisingly pleasant. Approximately 2/3 of a distribution will fall within 1 standard deviation of the mean. 68% is the more commonly used value there. If we spread out to within 2 standard deviations of the mean, and we think about all the information that falls, all of the scores in the distribution that fall anywhere in the part that I just shaded in red, it turns out that just about 95% of the distribution falls into that. And if we take this all the way out to the 3rd standard deviation, right? All of this, 99.7% of all scores are within 3 standard deviations of the mean. That kind of predictive power, the way that we can use the standard deviation to describe the shape of a distribution, is very useful. And so statisticians developed a system called a z-score, which allows us to interpret a standard deviation or a score in a distribution where we have a mean and standard deviation by playing a shifting game. I can take the mean, I can slide it over to be 0. I can take the standard deviation, I can rescale it, make it smaller or larger, and specifically make it a size 1. And then I get a representation. Starting at the mean, how far do I need to count in terms of number of standard deviation to get to the point that I care about? So if I care about a point that is right here, well, that's 1 standard deviation and about a half a standard deviation, 1.5 standard deviations above the mean. We can call that a z-score of 1.5, 1.5, and that's a simplified way of talking about this. Z-scores, once again, something we're going to build on quite a bit as the semester goes onward. For right now, just being able to calculate it is good enough. So a z-score, when you have a sample, like I have this set up, we will write that z is the deviation from the mean, x minus x bar, scaled in terms of standard deviations, so divide by s. And there's an extra line that got thrown in there, sorry about that. Or if you have a population data, you can take x minus your population mean mu and divide by the population standard deviation sigma, and you get a z-score just as easily. They work the exact same way. I like using z-scores as a tool for comparing results in 2 different distributions. On the first test, the class average was 78 with a standard deviation of 7. On the second test, the class average was 72 with a standard deviation of 12. And so we're going to ask which score is better compared to the rest of the class. A 91 on the first test or a 92 on the second test. Now, again, as far as raw scores go, right, a score of 92 is a higher score than a score of 91. That's obvious. There's nothing changing about that. That's not the question I'm asking. The question I'm asking is, if you think about the other students in the class, is it more likely that you scored better than a classmate if you scored a 91 on the first test? Or is it more likely that you scored a higher score than your classmate if you scored a 92 on the second test? We don't have just the score on your test. We have information about the class average as well. So we want to use that to try to make this a more interesting question. And we'll do that by way of z-scores. Compared to the class average on the first test, let's call that z sub 1, z-score for the first test. The score I'm talking about is a 91. The class average was a 78, and the standard deviation was a 7. That's a pretty straightforward calculation to perform. 91 minus 78 is 13. 13 divided by 7 is 1.86. Then, on the second test, we'll call that Z2. The score we care about is a 92. The class average was a 72, and the standard deviation was 12. 92 minus 72 is 20. 20 divided by 12 is 1.67. All right. And so we see that the z-score for the first test is higher than the z-score for the second test. And that makes an interesting interpretation. On the first test, we got a smaller overall score. The raw number on our score was a smaller number, 91 versus 92. But at the same time, on the first test, the class as a whole did better, 78 versus 72. So the fact that our score went up on the second test while the average went down plays a lot in our favor. We also have to think about the spread. Scores on the first test were a lot more closely packed. Scores on the second test were a lot more spread out. And in fact, scores on the first test were so tightly packed that even though we were a smaller amount above the average score, we did better than more people because the scores on the second test were that much more spread out. There are more people who did even more better above the average. There are also, unfortunately, more people who did worse below the average on the second test. And so since the z-score for the first test was a higher number, the z-score was a higher number, even though our score was lower and our score was closer to the mean, because the cluster was so much tighter, we are more likely to have done better than more of our classmates on the first test than we did on the second test. I don't grade on a curve in any of my classes, mostly because I don't have enough students to make it worthwhile. But if I were grading on a curve, that 91 would curve higher than the 92. In this case, I think they would both curve to an A. Usually when I see a curve done, the threshold is anything bigger than z equals 1.6 is an A, although I've seen other scores used. If I set z anything bigger than 1.75, then the first test was an A and the second test was a B. But again, I do not grade on a curve in my classes, so it's not specifically something you have to worry about. While we're on the subject of z-score, these are useful for talking about standardized scores. For example, the SAT math score. On the SAT, you can get a score somewhere between 200 and 800 on each of the parts. The math then has a mean of 500 and a standard deviation of 100. The verbal has the same thing happening again. The way that SAT scores are calculated, and several other scores that use a standardized score, but SAT seems to be the one that people taking statistics are most immediately familiar with. Um, the way that SAT scores are calculated is we're going to look at your score on your test. So let's say on the test that you took, the average score, using the scoring of multiple choice questions, correct equals 1, incorrect is negative 0.25, and blank is 0. Let's say that the average score was 78 and the standard deviation was 14.5. And your score was 85. With that information, I can calculate that your z-score was 85 minus 78 divided by 14.5, which my calculator is quite happy to tell me is 0.483, right? My score X is 85, had 2 digits. My z-score that I calculate, I'm going to give 3 digits. Now, using what I know about what the SAT wants us to have, we're going to use and assume that the z-score stays the same. So my z-score is still going to be 0.483. My SAT score, I don't know. I'm going to call that capital X. I know that the mean of my SAT score is 500, and the standard deviation of my z-score, of my SAT score, is 100. I have to do a little bit of algebra, multiply both sides of the equation here by 100, and then add 500 to both sides. And I get that the score, my SAT score, should be 548.3. I think that SAT scores round to the nearest 10. They used to, but it's been 20 years since I've really thought about it. So this particular person got an SAT score of 550. And again, that's certainly not the only application. IQ tests, any standardized assessment, ACTs, those sorts of things, all use this sort of process. It's also used in medical applications. We use it as a way of calibrating and talking about your measurement compared to the population versus your measurement as a raw number. Sometimes one or the other is more useful. But if we want to standardize a score, we can use a process like this. We can use this kind of a process in general. If we have a distribution with a known mean and standard deviation, and we want to change the distribution so it has a different mean and a different standard deviation, we can calculate a z-score, we can use that z-score in the new distribution, and we can get a new raw score out from it. Right. When you want to compare an individual data point, it's worth going through this much work. If you're trying to compare the spread of a distribution in general, sometimes it's a little bit messier. The raw value of a standard deviation is something that we can compare if we are measuring the same sort of thing, right? If I am measuring your scores as percentages on the first exam, and I'm measuring your scores as percentages on the second exam, scores as percentages is the same thing. I can compare directly the standard deviations. If I'm comparing your score out of 120 points for the first exam and your score out of 150 points for the second exam, now the number of points available is different, so the meaning becomes different. And thinking about ways of comparing standard deviations in that case is a little bit less obvious. And so that's why we have a tool called the coefficient of variation. Right. We will abbreviate coefficient of variation CVAR. It is 4 characters, 2 capital, 2 lowercase. It is still a single variable. And we can calculate this for a sample by taking the standard deviation, dividing by the mean, and multiplying by 100. And if we have a population, it works the same way. We can take the standard deviation, we can divide by the mean, and we can multiply by 100. Before I even read this out loud, I do want to stress that when I'm recording this video, this data is old, and this video may have been recorded sometime before you were watching it. So who knows if this has any bearing in current reality, but at one time in the United States, the average adult male was 68 inches tall, and the standard deviation of the heights of adult males was 5.8 inches. In Japan, the average adult male is 168 centimeters tall with a standard deviation of 16 centimeters. And so the question is, we could do the unit conversion to figure out whether the United States or Japan has the taller average height, which is certainly something you can do if you're so inclined. Again, I'm not sure that these data points came from the same year, so I'm not sure how fair of a comparison it is. Um, but what I am interested in thinking about is the standard deviations. Is the variation of 5.8 inches larger or smaller than the variation of 16 centimeters, given the discrepancies in the heights? This is a place where the coefficient of variation can shine. So we will take our standard deviation, we will divide by our mean, and we'll multiply that by 100. To get a coefficient of variation of 8.5. We will take our standard deviation in Japan, 16, divide by our mean, 168. We'll multiply that by 100. And we will get a coefficient of variation here of 9.5. All right. So at the time that this data was collected, again, I don't have a year attached to it. I have no idea if this is accurate current data or not. That's certainly not the point because this is math class, not population dynamics class. But at this point, the average height of adult males in Japan had a greater variation than the average height of adult males in the United States. Does that mean anything? I don't know. I don't care. What matters is we can say it. We can do the calculations, and it's up to the people collecting data to tell me whether the data is valid for anything or not. I'm not worried about that. I've got one last idea for today. I led off the day with the empirical rule for distributions based on a standard deviation. There are a couple of ways I can refine that we'll be getting into as the course continues. For right now, the one that I want to think about is Chebyshev's theorem. All right, Chebyshev's theorem very simply says that the proportion of values from a data set that will fall within k standard deviations of the mean will be at least 1 minus 1 over k squared for any k greater than 1. Right. The key idea here, the reason that this is useful and worth talking about, is that this will hold for any data set. The empirical rule that we started off today with relied on a normal distribution, a nice bit of symmetry. But as an example, we were looking earlier at that score in the class, right? The class average was a 78, our score was a 91, and we got that Z was something like 1.86. If we plug that value in for K, 1 minus 1 over 1.86, my calculator is very happy to tell me is 0.46. All right. So if the distribution of scores in the class is not normally distributed, if it is not symmetric, that means that I can still be sure that at least 0.46 or 46% of scores are closer to the mean than my score, right? Or put the other way, at most, the rest of it, right? 100% minus 46% is 54%. At most, 54% of people scored further away from the average, either higher than the average or lower than the average than what I did. But 46% of the scores are within the range that I set, the distance from the average that I set. Chebyshev's theorem is a nice approximation tool to have in your back pocket when you're talking about a distribution and you don't really know much about it. As far as building on from this, unfortunately, Chebyshev's theorem isn't all that valuable. The coefficient of variance is not all that valuable. They certainly have their places. The z-score that we talked about earlier is, again, going to be a tool that we find valuable and we find uses for throughout most of the rest of the semester. But that's all that I have on this idea for now. We'll come back, we'll talk about variance and standard deviation more several times throughout the course. But I'll end this video here. Thank you as always for joining me, and I'll see you next time.